So last meeting, we answered up to number 3 for strain. So today we'll just continue with problem solving. Now on to number 4. Number 4, an aluminum bar having a cross-sectional area of 0.5 inch squared. So I'm going to write that down immediately. Area 0.5 inch squared. Let me just move this. And then carries the actual loads applied at the position shown in the figure. As you can see, compute the total change in length of the bar if E is 10 times 10 raised to 6 psi. So again, I'll just write that. 10 times 10 raised to 6 psi. And then assume the bar is suitably braced to prevent lateral buckling. So lateral buckling is when your bar curves or fails along its length. Now that's an additional computation, okay, if we consider that. But again, according to this problem and for most of our problems with strain, you won't really have any lateral buckling, okay? So we've written the given. The question is change in length of the bar, total change in length, because we have 3 segments and divided into 3, 5, and 4 feet. Each of them will deform depending on the load it experiences. And the question is, what is the total change in length? So to compute for that, we need to get first how much will each bar deform and then just get the sum of that. Okay, so now the goal is first to get how much each bar deforms. And remember, our equation for deformation is PL over AE, right? L given, A given, A given. So now the question is P. Now for situations like this, if you've noticed, this is kind of similar to our stress problem, right? Wherein we have a bar and we want to know the stress in each segment. Now we want to know the strain, the elongation in each segment. So the process is kind of similar, wherein to get the stress, you get the internal load for each segment, right? So same thing here. To get the deformation, you also get the internal load corresponding to each segment. And recall, to get that, what we do is we cut, isolate. So let's start with the leftmost segment. I'm going to cut, isolate. So cutting this way, right? And then there's an applied load, 6,000 over here. Right? Again, I'm going to cut here. So that's the only thing included. And then wherever you cut, again, this applies to every kind of material or object. Wherever you cut, there's going to be an internal load that comes out. Okay? And you can call that P1. Since there's no material here, I'll just call that P1. Internal load for segment 1. Okay? And then let's complete all of our drawings. Let's now consider the middle segment. Cut in half and then you isolate either the left or right, up to you. Let's try isolating the left. So I'm gonna cut here, then you have this, right? Again, there's a 6,000 pound load to the left. And then again, if I cut here, as you can see, there's this 7,000 pound load on this intersection or interface. So I should include that as well, and then you have the 7,000. Right? And again, wherever you cut, there will be an internal load. And this still includes assumption of directions. Here it's easy to assume the direction because again, everything should be in equilibrium. If I have an applied force to the left, the internal load should be to the right to balance that out. Now here, upon looking, right, 7,000 to the right, 6,000 to the left, I need another force to the left to balance this out. So I'm going to draw this internal load to the left as well. And I'll call that P2. Okay? And then finally, this third segment, again, you're going to cut and isolate. You can isolate the left side or the right side. But as you can see, right side is so much easier. So I'll do that. Okay, isolating the right. Okay, I have this. And you have an applied load of 4,000. And once again, this is the only thing you can see upon cutting the right side. So there's nothing else, and then there's going to be an internal load here. This force is to the right, therefore my internal load should be to the left. And then I'll call that P3, right? Then let me just move this for space. Now that we have our sections, we can start solving for these internal loads. And to do that, we'll just use equilibrium equation, specifically summation of forces equals 0. Again, sign convention applies. To the left, therefore, negative 6,000. To the right, therefore, positive P1 equals 0. Therefore, P1, 6,000. Positive, therefore, correct assumption for direction. And then conclude whether this is tension or compression. Everyone, please answer. What is P1? Is that in tension or compression? Okay, very good. Everyone got it correct. It's tension. Because again, tension for forces away from your member. So just note that here, that's in tension. Later on, that's going to become important. All right, next, let's move on to the middle segment. Same thing, summation of forces equals 0. Negative 6,000. Positive 7,000 since to the right. And then negative P2 since to the left. And then upon solving for P2, you'll get 1,000 pounds. All right, P2, is this tension or compression? Once again, everyone answer in the chat. All right, very good, everyone. That is indeed compression. So we have compression for forces towards your segment. Right. And then finally, we have this summation of forces X equals 0, negative P3, and plus 4,000 equals 0, and then P3 is just 4,000. And we already know force away from your segment, that's tension. Okay, now, that's not our answer yet, but that is your internal loads. Next step is to solve for deformation. Okay, so total deformation is just the sum of all of these individual deformations. Okay, and then recall the equation for deformation is PL over AE. Okay, so you can solve it this way. P1 L1 over A1 E1 plus P2 L2 A2 E2, etc. You can do that. But if you've noticed, area and E, modulus of elasticity, is the same for all of my members. So all of them will have the same AE, all of them will have the same denominator. So I'll just write it this way. And they all have the same AE, which is 0.5 inch squared, and then E is 10 times 10 raised to 6, right? Same denominator, I'll just write it this way. And then just add or subtract in the numerator. Let's start with the first segment, right? So that's P1 L1. P1 being 6,000 pounds. Now this is where your tension, compression, tension is important. Because remember, sign convention, tension is positive, compression is negative. So apply that here as well. So 6,000 pound tension, therefore that's positive 6,000. Length is 3 feet. Now remember, we need to have consistent units. We're usually following the unit of E, which is pound per square inch. So I should convert feet to inches. To convert that, just multiply by 12. Okay? Next, 1,000 pound for P2, that's in compression. So there should be negative P1, P2 L2. So negative 1,000. And then L2, 5 feet. Once again, convert to inches. All right? So just times 12 once more. And then lastly, P3, tension. So that's positive. 4,000 times length 4. Again, convert to inches. 12. And then from this, please solve what's total elongation. Correct, Angelo and Nazareno. Judilia, Maligalig. Very good. Judilia. All right, it's 0.07. And then our unit, again, PSI, pound per square inch. Therefore, this unit is in inches. All right, and that's it for number 4. Now, remember, I can only do this if the cross-sectional area and modulus of elasticity for all of these segments are the same. Obviously, if they don't have the same cross-sectional area, I can't do this. I have to separate my terms, which is what we'll do for the next number. Before we move on to number 5, though, do you have any questions for number 4? Please answer in the chat. Okay, no questions. Great. Let's move on to number 5. As you can see, just on the drawing, number 5 has different cross-sectional areas, so I cannot do this. Okay? No, so let's read number 5. A bronze bar is fastened between a steel bar and an aluminum bar as shown in the figure. Actual loads are applied at the positions indicated. So if you're P, 3P, 4P, etc., find the largest value P that will not exceed an overall deformation of 3 millimeter. Once again, let's write the given as we go. Deformation 3 millimeter. Right? Let me just move this down. So that's delta 3 millimeters. And then following stresses, 140 for steel. So that stress sigma for steel is 140 MPa. And then we have 120 for bronze. So sigma, I'll call that BR for bronze, 120. Okay. And then 80 for aluminum. So sigma AL 80. And then assume that the assembly is suitably braced to prevent buckling. Again, that's bending or failure along its length. And then use the following modulus of elasticity. Steel 200. So EST 200. Let's see what's for bronze. We'll move this here. EBR is bronze, EBR 83. Okay, I'm just lining it up so that it's easier to see the values. And then for aluminum, 70. Okay. So unlike question number 4, where we're looking for total deformation, here we're given deformation. We want to see or figure out what value of P can we have. Right? So the initial steps of this are similar to how you usually solve for connected bars, where you figure out its internal load. Okay, so let's start with that. So steel, and I'm going to separate the steel part. So this is P. And once again, wherever you cut, there will be load. So I'm going to draw this to the right because this is to the left. And then this is steel, so I'll just call this PST for steel. Okay? Next, bronze, cut, isolate left or right, up to you. I'll isolate left. Okay, so like this. So bronze is a bit thicker. And then you have this steel. Right? Again, there's P on the left. And aside from that, there's 3P over here as well to the right. So you should include that in your isolation. 3P. And then again, wherever you cut, there's going to be internal load. So over here. Again, you can just guess where this direction is. It doesn't matter. Or you can make an intelligent guess because we already know this should be in equilibrium. There's 3P to the right, 1P to the left. So I need another force to the left to put this into equilibrium. Okay? And then this is bronze. I'll call this PBR. Once again, you can just randomly guess the direction of that. Doesn't matter really, because you can figure out the correct answer when you're done. And then we have this aluminum. Again, you can isolate left or isolate right. Obviously, the right portion is so much easier, so I'll isolate that. Okay. And then we have to the right, 2P. And then, again, there's going to be something here. So this is to the right, so I should draw my internal load to the left. And that's aluminum, so I'll call that PAL. Okay, so those are my drawings. So similar to what we did before, now let's create equations for that using your summation of forces. Okay, let's start with the leftmost. Summation of forces X equals 0. Negative P plus PST equals 0. Therefore, PST is simply P. Okay. Next. This is in tension because away from your object. Next, middle part, summation of forces X, 0, negative P, 3P minus PBR equals 0. Therefore, PBR is 2P, right? Towards, so compression. So let's say you guess this randomly, right? I guess this to the right instead. And then this is going to be positive. Your answer, the resulting answer here would be negative 2P. Okay? And then what you're going to do after that is, since that's negative, that means this is wrong. So just correct that. PBR, therefore, should be 2P. Instead of tension, that should be compression. Okay, so that's all you have to do if you just guess randomly and you guessed wrong. But we guessed right, so let's just keep that. And then finally, we have this. And summation of forces 0, negative PAL plus 2P. So PAL equals 2P, and then away, so that's in tension. Okay, now we have to know what's the next step. So we have all of our equations for internal load for steel, bronze, and aluminum in terms of P. And then as you can see here, we have all of these conditions. Remember, the amount of conditions or stress and elongation that we have is equal to the amount of equations that we need to test. So we have 3 stresses, so 3 equations, and then we have another equation for deformation. So you can just solve for each after that. Let's try starting with stress first. Okay? So stress is simply P over A, remember? Basic equation for stress. So PST over AST. Okay? So this is given 140 MPa. PST is P, so that's P over cross-sectional area. It's given 480. Okay? And then from this, please solve what's P. Correct. Vince and Alexia, Nugid, Cruz. Okay, good. 67,200 Newton. Right? Because this is Newton millimeter since MPa, and then this is millimeter. So you're left with Newton. That's not our answer yet. That's just a possible answer. And then next, let's have this one. Right. Stress bronze equals internal load for bronze over cross-sectional area of bronze. This is 120. PBR is 2P over cross-sectional area of bronze given 650. From this, please solve what's P. Correct. Mary and Angelo. De La Cruz. Maligalig. De La Cruz. Maligalig. There. 39,000 Newton. Again, not final answer. That's just a possible answer. Alright. Let me just move this up. And then we have this for aluminum. So stress in aluminum is simply internal load in aluminum over cross-sectional area of aluminum. That's 80. equals P, that's 2P, over cross-sectional area 320. Okay, from this, please solve what's P. Correct. Greg and Mary. Pineda de la Cruz. Okay, good. Pineda de la Cruz. Pineda. Okay. 12,800. Once again, Newton. Now, we're not done because this is only testing for stress. We have to test for this given uh, deformation as well, okay? And then to solve for that, let me make things smaller. Okay, I'll just move this back here because I don't have space anymore. And then this way. Okay. Okay, so that's only testing for stress. Now let's test for, again, deformation. So to test for deformation, again, this is the total deformation of all of these segments. So that's your sigma t. Okay, and that's equal to 3 millimeters. And remember, total elongation is simply the summation of PL over AE. Okay, so summation of PL over AE. Okay, and we can't do what we did earlier where all of this is just AE. No, we have to do it individually now. So let's try doing that first. So let's start with steel. So I'll just write here PL over AE and then create this line, right? So this means all of these values are for steel, okay? And then let's check, this is in tension, therefore this is positive. Next, aluminum, or rather bronze. Looking at bronze, that's compression, so this is negative, okay? And then PL over AE for bronze. And then for aluminum, that's in tension, so this is positive. PL over AE for aluminum, okay? Now let's just sub in our values. Again, total is 3 equals P for steel is just P. Total length, 1 meter. So I'll write 1. And then our E is in GPA, which you can convert to Newton millimeter if you want. And that's just times 10 raised to 3 to get Newton millimeter. So since Newton millimeter, I have to convert this into millimeter as well. So that's just times 10 raised to 3 or times 1,000. All over cross-sectional area already in millimeters, 480. And then E for steel, 200. GPA times 1,000 to convert to MPa or times 10 raised to 3. Okay? Next, minus P for bronze. So let's check bronze is 2P. 2P times length of bronze, 2 meters. So 2 times 10 raised to 3 to convert to millimeter, all over A, cross-sectional area given 650. And then modulus of elasticity, 83 times 10 raised to 3 to convert to MPa. And then we have plus P for aluminum, that's 2P. Length of aluminum, 1.5. Again, times 1,000 to convert to meters, millimeters. And then cross-sectional area, 320. And then 70. Okay, and then that's it. From this, please solve what's P. Correct, Vince and Hans. So Conde and Cruz. Okay, correct. It's 42,733.51 Newton. Again, that's just a possible answer. Okay. So from all of the choices, right, 67, 39, 12, 42, what should be our final answer? Everyone answer in the chat. What's the final answer here? All right, very good. Almost everyone got it correct. The final answer is 12,800. Once again, when choosing for maximum force, you're going to look for the least value. Okay? 12,800. Now again, if you're wondering why am I looking for the least value, if you're looking for maximum force, that's because anything greater than 12,800 will cause the aluminum bar to fail. And we don't want any failure in our structure. Okay, so that's it for number 5. Do you have any questions for number 5? Please answer in the chat. Okay, no questions. Great, let's have number 6. Okay, 6. Number 6, the rigid bar ABC shown in the figure is hinged at A and supported by a steel rod at B. Determine the largest load P that can be applied at C if the stress in the steel rod is limited to 30 KSI. Stress in steel, 30. So let's write that. Okay? So stress is sigma in steel, 30 KSI. And the vertical movement of end C, which is this, must not exceed 10 inches. Vertical movement. So you can write that as D, right? Vertical displacement, or you'll know that that's also just this. Displacement can also be written as delta. And again, that's 0.10 inches of C. So I'll write delta C 0.10. Okay? And so those are our conditions. We have 2. We have one for stress, one for deformation. So you gotta create 2 equations. Now, where to start? You can decide what you're gonna solve for first. So you can start again either stress or deformation. Let's try starting with stress. So based on your stress, okay? Now the equation for stress is P over A, right? And that is for steel. Cross-sectional area of steel is given, so no problem there. My problem is getting P for steel, okay? So to get P, that's the internal load of steel. Like what we did before, I need to create a free body diagram involving that steel. Okay? Which is easy enough because that steel is kind of like a rope, right? Where you cut, if you cut that rope, there'll just be this force outward, which is your tensile force. Okay? So let's draw a free body diagram based on that. So, okay, we have P here. And then if I cut, I'm gonna isolate this portion, right? Wherever you cut, there's gonna be force there, and that's the force within your steel. So I'll just write that as PST. Okay? And then there's a hinge there. Remember for hinges, there's always a vertical, or not vertical, horizontal. The more appropriate term is parallel and perpendicular to the surface. So this is your surface. Parallel to that is this way. So I'll just call that your vertical reaction at A. And then perpendicular is this way, and I'll call that your horizontal reaction is at A. And then that is your free body diagram. Again, the goal here is to get PST. Can anybody tell me what should I do to get an equation for PST? Having this free body diagram. So, correct. Vince and Mary. De La Cruz and Cruz. It's moment. Okay? So I'm going to use moment. Specifically, moment about your support, A. So summation of moment at A is 0, because usually we only take moment at these supports. So the only support here is A. And also, because I can remove these reactions then. I don't want to solve for these reactions, so I'll just take moment at that point. And then let's solve. Let's start with PST, rotate about A, that's counterclockwise, so negative PST. And then let's include these distances. This is 2 feet, this is 3 feet. There, right? And then that's perpendicular distance to A, it's 2. Next, let's have P, rotate. That's clockwise, so positive P. Perpendicular distance to A, that's 2 plus 3, so 5. Okay, and then from this, you can create an equation relating PST and P. You'll know that PST is simply 5 halves of P. But that doesn't really help me. I haven't solved for PST. So, I'm not done yet. You can just call that equation 1. And then remember, you have something else to help you. You have this limitation, stress. And we're solving based on stress. So now that you have this equation, you can start solving for it. Stress is simply P over A. I'll write that here. Stress P over A. Stress is 30 KSI. I want that in PSI. So KSI to PSI, that's just times 10 raised to 3. Okay. Equals PST. So this is stress ST, PST, AST. PST is simply 5 over 2P. So I'll write that 5 over 2P over cross-sectional area of steel, which is 0.50. From this, please solve what's P then. Correct, Nathan? Who else? Wala pang recitation. Okay, correct, Antoinette. 6,000. The answer is 6,000. So this is the maximum load it can carry, only considering stress. So once again, that's not our final answer yet. That's just a possible answer. The question is largest load P. So now we have to check for deformation. So now let's have this based on deformation, okay? So same thing, right? We know that the equation for deformation is PL over AE. However, this is only for materials. This is not the equation for displacement. This change in C is just the displacement of this point, okay? So you can't say, delta C is PC LC over AC EC, and then point 10 PC LC, etc. You can't do that because first of all, there's no length of C. There's no material there. That's just a point, and that's a displacement. So that's not the right process. Okay. So what now? I'm given this displacement at C. So what you can do is figure out how that displacement relates to your system. Okay. So let me draw what will happen. So once again, you have your system this way, right? Let's make it longer. And 2, 3. Okay. So you have this as your PST. And then here you have your load P. Okay. And then let's include again that 2 and 3 feet. 3 feet. Okay, this is point C, B, A. Same thing here, A, B, C. Okay, now what? You have to imagine how this deforms. So there's this applied load P here. Therefore, this rod is gonna move downward. Now, this is a pin, okay? So that's a pin. If you can imagine, if you have a pin there, that means this rod is free to rotate, okay? So at this end, it stays in place because there's a support there, but it can rotate. So that means this entire thing will move this way, okay? And so from this, it's gonna pivot this way, right? Because of this, it's gonna pull this entire thing downward, okay? So until you reach a certain final point. So let's say that's there, okay? And then that's the final position of this rod. You can say that this is how much point C displaced, and that's your delta C. And look here, at this point is attached to the steel rope. If its final position is this way, that means your steel elongated from this point to this point, right? Therefore, you can say that that is the deformation of your steel, okay? So this is your displacement of point C, deformation of your steel rod. And you have a certain shape there. Again, the goal here is to get or to relate this to the other parts of your system. Can anyone tell me what equation should I use to relate this to the other system now that we have this kind of drawing? Correct, Christopher and Vincent de los Santos. So Garcia de los Santos. We have triangles, right? And specifically, we have this triangle. We also have this larger triangle. And we call them similar triangles, okay? So by theory of similar triangles or by ratio and proportion, so I'll just call that by R and P, that's ratio and proportion, right? If you have two similar triangles, side over side equals side over side, okay? So let's take this one. Yeah, this, and then let's have this. Oh, I don't like that. Okay, there. So considering this green right triangle, side over side, let's take height over base. So that's height, which is your deformation in steel over base, which is 2, equals the height over base of this larger triangle, okay? And that is height, displacement of point C over total base 5. Okay. And then from this, you can create an equation wherein deformation of steel is simply this, which is given to be 0.10 over 5 times 2. What's the answer? Correct, Nathan? Who else? And Naomi. Reynes Cassie. 0.04. Now what am I gonna do with this? Right? Why do I care about deformation of steel? Well, you care about that because steel is actually a material. So that means I can use the equation PL over AE. Okay? So you can't use PL over AE at point C because again, that's not a material, that's just a point. Okay? But now that I have a value for deformation of steel, I can use PL over AE of steel. Okay, so 0.04 equals PSP. So PSP, but we have an equation for PSP. That's 5 over 2P. Now, these are still the same systems. So this summation of moments still applies. Okay? So I can still use that here. Instead of PST, I'll use 5 over 2P since P is what we're looking for. And then length of steel, 4 feet. Again, I want to convert that to inches, so times 12. All over cross-sectional area, 0.50. And then 29 times 10 raised to 6 for E. PSI, so no need to convert. From this, please solve what's P. Correct, Antoinette. Who else? P 412.50. Okay, correct. Jose. Francisco and Cabrera. Oh, why did you get different answers? Let me double check. Why are you getting 12,000? Five hours times 4 times 12. That's 4,000. So the answer is 4,833.33 pounds. Okay, again, that's a possible choice. So from this two, which should be our final answer, everyone answer in the chat. What's the final answer? 6,000, 4,000. Okay, very good. Almost everyone got it correct. The answer is 4,000. 4,833.33 pounds. Again, when choosing for maximum force, you choose the least value. Because if you use 6,000, okay, the deformation that you'll get will be greater than 0.10. And again, that's our limit. That shouldn't happen. So you should choose the lesser value. Okay, so that's it for number 6. Do you have any questions? Please answer in the chat. No questions? Great. Let's have number 7. Second to the last item. It's a bit more complicated version of number 6. So for number 7, the rigid bars A, B, and C, D shown in the figure are supported by pins at A and C and the 2 rods. Determine the maximum force P that can be applied as shown if its vertical movement is limited to 5 millimeters. A vertical movement of P limited to 5 millimeters. So once again, I like to write the given as I read. I'll just write that as delta P 5 and neglect the weights of all members. Okay, great. That's it. That's the only given. So there's only one limit here, which is your displacement of P. So there's only one equation to check. Now the problem here is I can't just do PL over AE. Because here at point P, again, that's just a point. You're just going to get displacement. So there's no PL over AE there. So you're going to do what we had earlier, where we need to relate this displacement to the deformation of the other members. Okay? Right. So let's draw what's going to happen there. So, okay, and then that's, so this is the original position, right? Okay, there's going to be this and this. P. And then if I cut here, that's going to release the internal load for aluminum. So I'll call that PAL. Okay? And then this is 3, 3 for dimensions. 3. Nope. Okay, 3, 3. Okay. And that is point A, B, C, D. A, B, C, D. Okay, let's draw what's gonna happen. We have this force downward. Okay. So this entire thing will move downward. Now, if you want an actual visualization of that, I can do that for you actually. Yeah, it's gonna move that way, right? So if you want to imagine from this, it's gonna move this way. Okay. All right. Uh, let's do that. Skew, and let's say that. Okay. And then let's remove all these unnecessary things. Oops. And okay. That's the final position of our things. So we can say that this, right, is the amount or the displacement of your point P. And at this point, that's attached to an aluminum rod. So initial point, final point, you can say that this elongated. And that's the displacement of your aluminum, right? Now what this is the tricky part, your steel. Now this is the original length of your steel, right? Now this is the original point of your steel for part B or point B, and then it ended up here, right? So you can call that your this part. That's the displacement of B. And then this is the original point of B, ended up here. This is the displacement of B. Now how does that relate to your steel? Because this object right here is your steel. Okay, so let's analyze it one by one. Right? So this part, again, this is the original steel part. If this point B ended up here, that means it created a compression in your steel, right? So you can write here, this is negative because it's in compression. And then at this part, this is where your steel ended, and then it went here. So your steel elongated. So that's a positive deformation because it's in tension. Okay? So now that's your free body diagram. You can leave it as that for now. So that's how you can create a relationship between all of your values. Now, before you do that, remember what we did here, right? What we did, we solved for moment first, because that's the easiest one to do, to relate your internal loads to the applied force. Let's do that here as well. Internal load to applied force. So let's start with bar AB. Okay. So again, just looking here, bar AB, summation of moment, right? Previously we did at the support. So same thing here, you're gonna do moment about the support here. Because again, this is a hinge, there's gonna be reactions this way or this way. I don't want to solve for that. And you don't even have to, because you can just take moment about A so that reactions cancel out. So moment at A equals 0. Okay? If you cut this part here, you can see, right? That's PAL. Rotate about A, that's counterclockwise, so negative PAL, perpendicular distance 3. Okay? Next, we have this for the steel. Now, what happens for steel? So, what happens here is, so let me just draw everything. This is your PAL. Here for the steel, you're gonna cut here, right? Wherever you cut, there's internal load. So there's gonna be a PST here. And then same thing here. If you cut this, isolate the bottom, there's also a PST. So just considering this part, There's a PST downward, rotate about A, that's clockwise, so positive PST. Perpendicular distance, 6. Okay. And then next you can create or simplify this, you'll say that PAL is just twice your PST. Okay. Now, next step, after creating your moment equation, right, we did ratio and proportion. So let's do that here as well. We're only focusing on AB, so this is the part that we're going to focus on. So by ratio and proportion, by R and P, right? Height over base equals height over base. So considering this height, sigma AL over base 3 equals height sigma B over base 6. Okay, not 3, okay? This is the entire base of that larger right triangle. Okay, and then what we do there is aluminum is an actual material, so you can rewrite that as PL. So PAL length AL, or rather, I'll just write it this way. PL over 3 AE for aluminum equals, so this is just B, right? Although that's point B, that's not the actual deformation of steel. That's just the displacement of point B. Okay, once again, this delta B is the displacement of point B. That's not the deformation of steel. Okay, so that means there's no PL over AE here. We just copy that, sigma B over 6. Okay? And then let's simplify, so you can see you can cancel out this. Okay? 3, 6. You'll have PAL, which is 2 PST. 2 PST times length of aluminum, 2 meters. So 2 meters, I want that in millimeters, so times 10 raised to 3 to convert to millimeters over cross-sectional area 500 millimeters squared. So no conversion, E70 GPA. GPA to MPa times 10 raised to 3 equals sigma B. Okay? Over 2. Right? Because 3, 6, so over 2. From this, you can create an equation relating deformation of B and internal force in your steel. Okay, can anybody give me the simplified version of this? What's the number here? Okay, correct, Angelo. Anyone else? Okay, I just need what's the relationship between delta B and PST. So you can just 2 times 2 times 10 raised to 3 over 500 times 70 times 10 raised to 3 times 2. Okay, correct, Hans. Conde. Good. It's 4375. Okay, now what will I do with that? Nothing. You can just call that equation 1. Okay. So now let's move on to the second part, your CD. So same thing, summation of moment. So here we did A, for this section we'll do C. So summation of moment at C equals 0. So P rotate about C, that's clockwise. So positive P times perpendicular distance 3. Next, also, we have this, right? PST now upward. Rotate, that's counterclockwise. So negative PST times perpendicular distance 6. There's no other force, so equate that to 0. And then again, simplify, you'll see that P is just twice PST. And then let's just call that equation 2, okay? Next is, again, ratio and proportion, so by RNP. So now focusing here, again, base over height equals base over height. Delta P over height over base 3 equals delta D, displacement of point D over total base 6. Okay, and then let's simplify this. Okay, so this is D. Twice delta P equals delta D. And then let's just call that equation 3. Because P and D are not materials, they're just points. Okay, so there's no PL over AE here. They're simply displacements. So I'll just call that equation 3. All right. So now we're done doing the ratio and proportion part moment. The only thing that's left is to try to analyze something else about your system. So we had an equation for deformation of aluminum. The only other material that we have aside from that is steel. We don't have an equation for the deformation of steel here, right? That's because it's a bit more complicated. You take it on this portion, okay? So once again, what happened to your steel is it compressed by this much, right? And then it elongated by this much. So to put that into equation, the total deformation of your steel is how much your steel elongated, and that's positive, plus how much your steel compressed, and compression is negative. And that amount is by this, delta B. Okay? Once again, total deformation of steel is over here. It compressed by delta B. This is how much it compressed, so that's negative delta B. You can also write it that way, negative delta B. And then it also elongated by this much, which is your displacement delta D. So plus delta D. You can write it that way as well. Okay. So that's why it's important to know, is it compression or tension? All right, and that is equation number 4. Now, what we want to do now is sub, 1, 3 into equation 4. Sub 1 and 3 and 4. Why? Because that's all that we need. This is your delta B, this is your delta D. And then you can create an equation for steel afterwards. So delta ST, which is your PL over AE. So PST, LST over AST, EST, or just PL over AE and then ST at the right side, equals delta D. So using equation 3, delta D is simply twice delta P minus delta B, which is this, 1 over 4375 PST. Okay? And then let's just sub in our values. PST as is, let's search for that. Length of steel given 2 meters. So times 10 raised to 3, convert to millimeters, over cross-sectional area of steel 300, modulus of elasticity 200 times 1000 to convert to MPa, equals twice delta P, and that's given. Delta P is 5 millimeters, so twice 5. And then minus 1 over 4375 PST. From this, you can solve what's PST. In decimal form, please. Oh, that's incorrect. Correct, Alexia. Who else? and hands, correct? 38,181.82. That's not our final answer. We're looking for maximum load P. But we have an equation relating PST and P, right? It's over here. So just sub that into. And then therefore, you're gonna get, let me just move everything. And therefore, P is just twice that, which is 76,000. 363.64 Newton or 76 kilonewton. Okay, correct, John? Yeah. Okay, and that's it for number 7. Do you have any questions for number 7? Please answer in the chat. Since there's no questions, let's have the final example for today, number 8. Okay. So for number 8, as shown in the figure, 2 aluminum rods, AB and BC, hinged to rigid supports, are pinned together at B to carry a vertical load P, which is 6,000 pounds. All right, let's write that. 6,000 P. What else? If each rod has a cross-sectional area of 0.60 square inch and E 10 times 10 raised to 6 psi, okay. So area 60, 0.60 square inch, and then modulus of elasticity 10 times 10 raised to 6 psi. Okay, and there. Compute the elongation of each rod and the horizontal and vertical displacements of point B. Assume alpha, theta, 30. Okay, alpha, theta, 30. Okay, so we're looking for 3 things. Elongation of each rod, so rod BA or AB, rod BC, and then horizontal vertical displacement of point B. Let's focus on the first part first, elongation of each rod. So we're looking for delta AB and delta BC. In order to do that, again, the equation is PL over AE. I need to solve for internal load P. And to do that, it's the same process as before. Draw a free body diagram, create equilibrium equations. So let's draw a free body diagram of this. There's a downward force P, because weight is always downward, 6,000. What else? We have these two, right? And then there's this angle, 30. Okay. Now you can randomly guess the directions of all of these, or you can make an intelligent guess. So this is downward. I need a force upward. Okay, I'm gonna take it from this one. Okay, here. And that's your, I'm gonna call that PC. And then I'm gonna call this PA here at the top. Okay, since this force is to the left, I need another force to the right to balance that. So I'm gonna draw this way. That's correct, John. Yes, it's that way. Okay, so this is my free body diagram now. Next step, equilibrium equations. So let's start here. Summation of forces, you can start X or Y, but I'm gonna do X. We'll see in a minute why. So Fx equals 0. PA to the right, so positive PA. I need horizontal component, so that's cosine theta. So PA cosine 30. PC to the left, negative PC cosine 30 equals 0. From this, you'll see that PA is the same magnitude as PC. Okay, and then, yeah, that's it. Next, you move on to summation of forces Y equals 0. Negative 6,000 Next, upward, therefore positive PA. Vertical component, so that's sine 30. This is also upward, so positive PC sine 30 equals 0. PA is the same as PC, or PC is the same as PA, so I can rewrite this as negative 6,000 plus twice PA sine 30 equals 0. From this, please solve what's PA. Anyone? Correct, Dave, Kalani, and Mary. 6,000. Positive, therefore correct assumption for direction. Right? PA is away from the point, so that's tension. And PB has the same, PC has the same value. So also 6,000. However, instead of tension, that's towards the point. So this is compression. And now that you have all of that, you can solve for elongation. Here. So elongation, let's start with A. Of rod AB is simply PALA over AE. A PA 6,000. Length of rod AB 10 feet. Again, I need that in inches, so just times 12. All over cross-sectional area given 0.60. And then E is given 10 times 10 raised to 6. Okay. And then the answer that you should get there is 0.12 inches. And then that is in, same thing as your PA tension. Okay. Next, let's solve for elongation of rod BC. Again, that's just PB, length AB, length BC rather, over AE. PB, PC. PC 6,000. Length 6. I need that in inches, so times 12. All over 0.60 times 10 times 10 raised to 6. Okay, and then you should get 0.072. Rounded off 0.07 inches, and that is in compression. Okay, and so that's the first part. Now the second part is a bit more challenging. Okay, so the question here for the second part is find the horizontal and vertical displacement of point B. Okay, so like what happened earlier where we have these points, and because of an applied load, it moved a new way. Same thing will happen here. Okay, so let's say we have that. And what's gonna happen there is it will move a certain way. So let me just cue that. It's gonna move that way, and not only that, there's also a possibility it's gonna move this way. Okay? So let me try to. Okay? And it's gonna move that way because of this load. And then therefore, this is the final point B. Okay? So let me just remove this. This is just the final point. Right? This is B. Right? I'll call this B prime. And then let's call this total displacement as X. And then This is the vertical and horizontal displacements respectively. I'll call this delta V and then delta H. Okay? And then let's call this angle phi. So one way to analyze this is this rod BA is an elongation. So if you try to draw that, extend it, and it's gonna look something like this in elongation, right? And that relates to this total displacement this way, okay? Let's use a different color. Oops. Okay. This is this amount, 0.12. Okay. So same thing here as well. Okay, if I try to extend this, draw a straight line from this point perpendicular to your original rod, and you're gonna have something like that. Again, this is a right triangle, right triangle. And this amount is the 0.072. Okay? And so that's how those deformations relate to each other. Now I need to get the value of x and phi to solve for delta V, delta H. So in order to do that, let's figure out these angles first. I'll call this alpha, I'll call this beta. Okay, and then we can isolate that. I'm gonna draw a shorter version. Okay. So that you can see clearer what's happening. Okay, this is the x, right? This is your alpha. This is 0.12. And then same thing here. Okay, I'm gonna isolate this part. This is your 0.072. Okay. Okay. 0.072. And then this is that beta. And this is your x. Okay. Now from this, you can create equations. Cosine alpha is simply 0.12 over adjacent x, hypotenuse x. In the same manner, cosine beta equals 0.072 over x. Now you can't solve for anything yet, but you can write beta in terms of alpha. How? Now recall these angles. Okay, this is 30 degrees. Therefore, this also 30 degrees. Now, if you've noticed, by the way, this beta up to x. And up to this line x. If you've noticed, if you combine these, this total angle is 180, right? So 180 minus 30 minus 30, you get 120. And then to get the beta, you're just going to subtract alpha as well. So that's 120 minus alpha. So I'll rewrite this instead of beta. That's 120 minus alpha equals 0.072 over x. Okay? You have two equations, two unknowns. You can solve for alpha and x. Okay? So from this, you can solve for alpha, which is 51.79 degrees, and then you can solve for x, which is 0.19 inches. Now that you have alpha, you can also solve for beta here as well. So you should get 120 minus 51, you'll get 68.21. Okay, now that I have alpha and beta, we can solve for phi. Now, in order to solve for phi, it's this way. So, okay, this entire thing is 90 degrees because this is just a vertical line, a horizontal line. So this is 90 degrees, right? So if I get beta plus 30, right? And then subtract 90 degrees from that, you'll be left with your phi. Okay, so once again, that's beta plus 30, right? Again, this is beta plus 30, and then you're going to remove the 90 degrees. You're left with phi. And then the answer to that is 8.21 degrees. And then finally, all right, let's start with delta V. That's just x. So this is adjacent to your phi, so x cosine phi. And that is 0.19 cosine 8.21. You should get 0.19 inches. And then same thing, delta H, x sine phi, since it's opposite to your phi. And you should get 0.03 inches. All right. And that's your answer. Okay. And then that's it for number 8. Do you have any questions for number 8? Please answer in the chat. No questions? Great. That ends the first part of strain. This Saturday, you'll just have homework. As you can see here, our schedule. So homework 2, I'll upload that by 12 midnight on Saturday. So no Zoom meeting on Saturday. You can just answer your homework, okay? And then next week, Tuesday, I think we still have classes next week. Next week, Tuesday, we'll just continue and finish this topic, strain, okay? Also, one more thing before I dismiss you. I've already rechecked all of your exams, gave you your grades. So that's your final grade already, except for those who hasn't passed or haven't passed requirements yet. I've also uploaded the IP exam, so please answer that. Again, if you want more details about what to do with the IP exam, or IP exams over here. So only for those who got I or IP should answer this. This is unlimited attempts. You can answer however you how many times you want. Please read instructions carefully. You don't have to upload solution for this, okay? So just answer this until your M1 for IP students grade turns to 70%. Okay, I'm gonna create that column later on. You still can't see it right now because I haven't done it yet. But again, in the future, maybe tonight, you'll see your grade column M1 or MG1 for IP students. Okay, so you're gonna solve IP exam until that grade column is at least 70%. Okay? Again, this is only for those with IP or I. Yes. Scores immediately pop up. If you got a grade of 0, that means you didn't follow instructions or your answers are just wrong. Okay? So again, this is unlimited attempts, so you can try and figure out where you went wrong. Okay? So yes, scores automatically show up each time you try. So again, please read instructions carefully. 2 decimal places. So let's say your answer is 1.2. Don't type 1.2, type 1.20. Okay? Because 2 decimals. That's just the formatting for Blackboard. Any other questions, concerns, clarifications? Also, for stress should be in MPa, not Newton millimeter squared. MPa. All right, no more questions? Okay, since you don't have any more questions, I'll see you on Tuesday. You may go. Goodbye, class.
Bye, ma'am. Thank you.
Ma'am.
Thank you po, ma'am.
Thank you, ma'am.
Welcome.